out. And so hopefully this set of notes, or excuse me, this set of vocabulary will be pretty straightforward just because some of it is so familiar. Protons, neutrons, electrons. So far we've been looking at chemical reactions. Chemical reactions, like I said yesterday, are dealing with electrons. So whether they're sharing them like covalent bonds or they're exchanging them like with our ionic bonds, forming ions, it's dealing with electrons, all right? The big difference now is that we're going to be looking at nuclear reactions. Nuclear sounds like nucleus. The nucleus has what two subatomic particles? What are found there? Not the electrons. Protons and neutrons, right? So that's what a lot of this focus is going to be on. Some of this is going to be very familiar, and then we're going to add in just a little bit of new stuff, okay? None of this is very difficult, this unit. I kind of hinted yesterday that a lot of times people really enjoy this unit. It is a very important idea because, well, today's election day, which is one thing. And obviously our government decides what our energy, sources moving forward are going to be. And so nuclear power is still on the table. Like, it's one of those ideas that's debated, whether you're talking like green energy or whether we stick with our old fossil fuel energy, which we know isn't going to be able to last forever, or what are some alternatives, right? And nuclear is one of those alternatives. And so we're going to talk about that. So it is important. You guys can actually have like an informed opinion on this. So sometimes things get kind of heated and debated in here because you're like, well, I think this is a great idea, or I think this is an awful idea. But you'll be able to see the pros and cons of using nuclear energy, as our power source. So that is important as you become adults and you start voting and you start making decisions. So kind of is interesting that we start this unit on the day that we actually have our midterm elections. So, okay. So we know that chemical reactions are involving electrons. Nuclear reactions are going to involve the nucleus. Did everybody get their new set of notes? Aiden?
Yeah.
Are you going to use it? Oh, you got them? Perfect. You were hiding them. Okay. And so nuclear reactions can actually involve much greater energies than any type of chemical reaction. So we think like a normal bomb, a combustion bomb, is big. It is, right? But if we look at nuclear bombs, which we will look at towards the end of this unit, they're not even a fraction of the strength that a nuclear bomb can have. So nuclear energy itself is an extremely powerful source compared to anything that we can produce chemically. Okay, so we're going to focus on three main aspects of nuclear activity. The first is radioactivity and isotopes. Isotopes is not a new idea, or are not a new idea. You've had this question probably 10 different ways, 10 different times throughout this year already. Isotopes are when you have an atom that has a different number of what? Has the number of electrons changed, the number of neutrons changed, or the number of protons changed in that atom? Nevaeh? The neutron, right? And I would say we're probably at about 85% of people are actually getting that right now. It was actually the last questions on your test. Again, I'm going to keep asking this question until we're closer to like almost 100% getting right that neutrons are the particle that changes when we're talking isotopes. We're going to also talk about nuclear fission, and we're going to talk about nuclear fusion. You probably have heard those words, whether or not you exactly know what's involved, but we'll get into those a little bit more. Bless you. All right. So we know that everything is bonded by particles, right? This is just background. We've talked about this. You've had it in 5th grade, you had it in 6th grade, you had it last year, you had it this year already. So this is familiar, which is nice. So atoms are made of subatomic particles. We have the proton, which are positive, the neutrons, which have no charge or neutral, and then finally our electrons, which are negative. Again, not new concepts here at all. I feel 100% confident that you guys all know this. Bet my life on it. That's how confident. And so we know that the nucleus is made of protons and neutrons. They're here in the center. And then it's our electrons that are on the outside. They are the ones that are kind of like buzzing around. If the nucleus is like the hive, the electrons are like the bees, kind of buzzing and moving all around. And so the amount of charge in the nucleus is going to be determined by how many protons. Because what we know that the protons are positive, right? So that makes the whole nucleus positive, right? And so if you have a lot of protons, you have a lot of positive charge, which only makes sense. We also call this the atomic number. Remember, the atomic number is the small number, small like the atom, and it only counts the one subatomic particle. It's only counting the number of protons. All right, so that same idea back from our first unit, you still need to have in your mind here. And then we know that the electrons, which are negatively charged, are attracted to that positively charged nucleus, and that's what kind of keeps the whole atom together, because we know that opposite charges attract. Again, this is an idea that you had a lot last year in 8th grade science, right? The positive and negative end of a magnet will come together, or that north and south pole. We know that if you have something that has a positive charge and something that has a negative charge, they will attract, and that's kind of what our static electricity is all about, right? That's why, you know, like a sock will stick to maybe your sweatshirt when you pull it out of the dryer, right? The sock has become negatively charged, the sweatshirt becomes positively charged as they tumble around and they get stuck together because opposites will attract, okay? So that's what's actually kind of holding the atom together. This positive center and then these negative electrons on the outside, that attraction, which is why the inner electrons are held more tightly and our outer electrons are able to get pulled off in bonding, right? So all of what we've talked about kind of fits together and still holds true, which is nice. We're not like changing everything we've already learned. Okay, and so protons and neutrons are packed tightly together. Jam-packed, which is why the nucleus of the atom had the majority of our mass of the whole atom. And so really the nucleus is super tiny compared to the rest of the area of the whole atom. So it's a very small amount of space that it takes up, but it is super, super dense, extremely tightly packed. Remember that funny little video, like with that weird little like astronaut guy, and he's like, the atom is really, really small. And the nucleus is the center. And like he's comparing everything, like where he had like the blueberry and you zoomed into it. This is kind of that same idea where you have the nucleus that is super densely packed, super small, but that's the majority of the mass. And then the rest of the atom is pretty much empty space, and you just have the electrons kind of buzzing around in that empty space. And so in that same video, it said like if the nucleus is a penny sitting on the 50-yard line, if the whole arena is, is our atom. Okay, so if you think of a penny sitting on the 50-yard line, I'll let you know how small that nucleus really is. And because it's so densely packed, even though it's really small, it's where most of the mass is for the atom. So that's why we call the number of protons and the number of neutrons our mass number, because it's the more massive of our numbers that we deal with on the periodic table, and it's including the protons and the neutrons. It's counting both of those things. So it's looking at the nucleus, not just the protons like the atomic number does, but the protons and neutrons. Again, nothing new here so far. All right, so here is where we start into something a little bit different that we haven't considered yet, right? Something called nuclear forces. It's just kind of generic, and it's called like the strong nuclear force, and that sounds kind of weird, but that's exactly what it is. All right, so the particles in the nucleus are pulled together by this thing, this force we call the strong attractive force. and it's between the protons and the neutrons. And you're like, well, that's weird, because why are neutrons have no charge, and then the protons have a positive charge? So it's not that charge is attracting them together, right? But that's why we call it a strong attractive force. What's really happening is this attractive nuclear force causes the protons and neutrons to kind of stick together. And it holds the nucleus as a very tightly packed, contained kind of area or space. And so the nuclear force is extremely weak at most distances. But over the very small distance of the nucleus, the force is great enough to kind of hold the neutrons and the protons together. So in my mind, I kind of think of this attractive or strong nuclear force as kind of like glue. It's the glue that kind of holds the nucleus together, okay? And that's really as in-depth as you need to understand it. It causes this nucleus to stay together, all right? So if you think of it kind of like Elmer's glue or rubber cement even, right? It's sticky and it's holding the neutrons and the protons together in that nucleus. Very tightly packed, very strong force keeping it all together. And you can kind of see that here, right? The neutrons, protons, They're not just like jumbled around loose. Like it's as tight as they can get while they still maintain, their own kind of shape, right? I think yeah. And so again, you can kind of see, normally, what do two positives want to do? They want to repel or push away. So you would think having all these positives jam-packed in the nucleus together, they would just push apart. And then we'd have chaos, right? No atom would ever be able to maintain, because the nucleus would always be kind of exploding, pushing away. But the neutrons kind of neutralize that, and it acts as like the atomic glue to keep that nucleus together, okay? And so if you start thinking, you're like, wait a minute, opposites attract, likes repel, there's full of a bunch of likes, it should be pushing away. It's the neutrons that overcome that, right? And so that's kind of like the atomic glue that holds it all together. All right, and so don't forget what we already know about these forces, and this is why this works. The positive protons really should repel away from each other, since their like charges should repel. Sorry, let me go back. That probably covers up some of your words. Okay, and so if you see this picture, we should expect the protons to do this, right? Repel. But the attractive nuclear force between the protons and the neutrons is stronger than that repulsive. So repulsive is just another word for like a form of repel, right? So that repulsive electrical charge between the protons is overcome by the neutrons. It's a pretty important thing that those neutrons can do. Because again, I'm not even sure, we wouldn't even have atoms. We wouldn't have stuff. We wouldn't have these elements if the nucleus couldn't stay together, right? And if the protons were able to repel like you would expect, would we not have atoms? What would it be? Can't even really wrap our minds around what would happen if the neutrons weren't able to overcome that repulsion. So the neutrons overcome that repelling characteristic of the protons. The way I think of it, the neutrons kind of neutralize that natural repulsion or that natural repelling property that the atoms would feel. Okay, and so if the attractive nuclear force isn't strong enough to keep the large nucleus together, that's when it will become unstable. And that's why we have this whole unit, because that's what we're going to focus on. Because sometimes the nucleus gets too big, and then that the neutrons can't really neutralize the whole nucleus as a whole. And without that, then it starts to kind of break down a little bit, and that's where we do get some changes happening in our atom. Okay, so far, everything is exact same as we've already learned, right? Protons, neutrons, electrons, atomic number, mass number. The only new wrinkle that we've added to this is looking at the nucleus itself. Protons are positive, they should repel. They are repelling, but the neutrons act kind of like as that glue that holds everything together because it neutralizes that natural repelling. Okay. And so this shows what's actually happening. So this is what we would expect to happen, and then this is what the neutrons do. Because they're there, it allows all the subatomic particles in the nucleus to kind of stick together. Good? All right. And so large nuclei are typically going to become unstable. And when this happens, they decay. And that decay gives off radiation. So a small nucleus like this, the neutrons are able to neutralize and keep everything together. The glue is sticky enough. When you get a big nucleus, it's able to keep like parts of it, but keeping the whole thing is more difficult. Okay, and so if it's not able to keep it all together, it will start to break apart. And so we call that breaking apart decay. Decay does not mean like rotten. Like a lot of times we're saying, oh, that animal on the side of the road was decayed. Like we're not saying it's rotten like that. We're saying decay means like breaking down. And so this will happen when a nucleus has a lot of protons and neutrons, and each proton or neutron is only attracted to a few of the other particles by that strong force. So here it's small enough that all of these are able to stay together. They're able to overcome the repulsion. But over here, they're not able to overcome it because it's too big. Like this section maybe will stay together, and maybe this section will, and this section will. But the whole thing itself is way too big. And so it's not sticky enough to keep the whole thing together. And so you might get like kind of chunks kind of separating, and that's the decay process. And sometimes if the protons are too far apart to be attracted by the strong force, then that repulsion will take over also. Because it's not like it gets rid of the repulsion between the protons, but it's able to overcome it. And so if it's not able to overcome it, then that repulsion kind of kicks in. And that's when the decay happens. Let's see something. Oh shoot, hold on. I have to go again.
If you're interested in learning about particle physics, one of the key topics you need to understand are the forces that come into play.
Let's go over here. All right. We're going to